Yes, welcome to the lecture of physics of rigid bodies. As you know, rigid bodies are about things that are rigid. Center of mass, as you can see, it follows a straight line on the spanner. Although you spin the spanner, it is turning. The movement is actually in a straight line. I have to say this for the audience at home. Right? It moves in a straight line because there's no other forces. This could be shot from the top, right? This picture could be shot from the top, so it does not have a horizontal force on it. So you see it's going in a straight line. Okay. Not an issue. Right. Let's look at the center of mass of a system of particles. Okay. You have a system of particles. How do you find the center of mass? This is the formula. Right? Basically, you take moments, it's something like moments, right? But actually, if you take the product of the mass and the distance from a reference point, you multiply. If let's say there's a mass to my right and a mass to my left, the mass to my right is positive x, the mass to my left is negative x, right? Then in 3D, you have x, y, and z. Okay, so let's do it for x, then y, and z, you get actually something like that. Okay, mathematically, it's not that difficult. Okay, divide out by the full mass, of course. Okay, so if you summation of summation I of mi gives you the full mass capital M. That's usually how we do it. Okay, then the center of mass factor, right, from where you are, right, is the summation of all these factors. Okay, that's just a mathematical representation. But the more important thing is how you apply it in real life. Okay. Let's try this, something a little bit easy, right? What's the center of mass of the planet, not planet system, right? So you can imagine imagine a light bar in between the two, right? And where would you balance this? It would be slightly closer to the bigger mass and hence heavier mass, right? Those who just came, you can come and take your notes and sign your attendance, right? So doing this, you can see using moments. If we let this distance be x, mp to where the center of mass is, be x, mp times x is ms d minus x. Okay, then you can get this. It's not a problem. Rigid body rotation, right? This is something that you don't have in your H2 physics, so I think it makes sense for you to listen a little bit closer here. It's actually quite simple once you get to know it. Right? I used to do this, I think, when I was your age, in the syllabus itself. Don't know why they take it off. All right. There are a few assumptions. Assumption is that the object is rigid. Right? If it actually is flexible, then the physics becomes really difficult. Right? And there's a pure rotation motion. Rotation about axis about fixed. So let's take O as a center, and everything else referred to with a distance r from it. Okay. Next, we say that everything is rotating with the same angular speed, and then same angular side. What does it mean? Angular speed is given by this symbol omega. Angular speed means that if one point, let's say this point P, rotates 45 degrees in a certain amount of time, another point will also rotate 45 degrees about this point in the same amount of time. Okay. Same angular acceleration means that if this point P speeds up in the angle per second, all other points speeds up by the same amount. Right? These are the assumptions that we are making. Because if not, the body is flexing. It will not be a rigid body. It will be a physics of rotational of non-rigid bodies, which will be difficult. Okay. Any questions at this point? Okay. So let's talk about some of the things that we want to think about. We know in your secondary school you learned about this formula, right? S equals to r theta. The arc is equals to r times theta, and theta must be in radians in case you have forgotten. Theta must be in radians. So if we have a distance, right, S is a distance, or in this case a displacement, we can differentiate it to find a velocity, right? So if you differentiate S to find the velocity, not a problem. You can differentiate theta to find the rate of change of the angle, which gives you omega. So omega is like velocity. It's like related to velocity in the sense that it's the rate of change of angles, right? And if you have velocity, then you have acceleration, and you have the acceleration of the angle, right? So this is what we call angular velocity and angular acceleration. Okay? Okay? Here there's a subscript t. What do you think it means? What does a subscript t mean? It means the tangential acceleration. Alright, that means tangential to the radius. Okay? Tangential to the radius. So the simpler questions that you will have is when the a t is equal to 0. Right, that would be a simpler questions. Those without are slightly harder, but always know that you can always map it from kinematics to angular momentum, angular velocity, these kind of questions. It's not a big problem. Right. This one you will learn in circular motion pretty soon. After your dynamics lecture, you will have work energy power by me. Then you will have circular motion by Mrs. Tan. Right? And in that situation, you will learn that the radial acceleration will be v squared over r. Right? And that will be given by r omega squared. And that is given in H2. Okay. Vectors. All right, right hand rule. Don't need to kill yourself over this. It's good to know. So some students say that since it's rotating, let's say the circle is moving, look at my hand, moving like this, the vectors of omega must be in this direction, right? In the direction of v, not true. The vector is actually pointing away, perpendicular to the plane of rotation. Okay, so you're rotating this way, your fingers travel this way, your vector omega is actually outwards. Okay, you will not see this in H2. Right? If you're rotating this way, clockwise, you actually is pointing down. Okay, so this is just some convention. So again, acceleration. So if upwards is this way, points upwards. If you're accelerating upwards, your acceleration is also going to be upwards. Your acceleration vector. When you're slowing down, acceleration vector is pointing down. Okay. Right. Is finite rotation theta a vector? Consider this. What's a vector? How do you decide something is a vector? It must be commutative. Do you know what commutative is? Okay, let me just show everything because you already have the notes. Huh? So commutative means that if you do A then B, right, is equals to B then A. So an example is this. If I pour hot water, then I pour my instant coffee in and I stir, I get coffee, correct? If I put my coffee powder in first, then I pour hot water and I stir, I get my coffee, yes? I switch the order of the sequence, it does not matter. If I put on my shoes first, then I put on my socks, that does not work, right? So the action of putting socks then shoes is a bit more of a vector, right, compared to, putting socks then shoes is not a vector because it's not commutative, whereas the action of pouring coffee powder and then water, those are commutative. We don't care about the sequence. Okay, so guys, also, if you want to propose to your girlfriends, please buy a ring first, then propose. Don't propose, then give the ring 3 days later. It doesn't work that way. they will remember it for life, and even if you do marry her, you not life experience. I'm a very I plan very well. Just saying. Sorry. Right, so rotation, is it a vector or not? If you look at this, if you rotate forward in the z direction and then you rotate in the x direction, whereas compared to rotating in the x direction, rotating like this, from z to x first, and then rotating from y to z, it's not the same. You end up with two different results, although you have the two same actions of rotation, just that the orders are switched. So a finite rotation is not commutative. The rotation is not a vector. Okay. Rotational energy. Rotation requires energy. Something that's not spinning at first and then spinning requires energy. If you do not believe me, all you have to do is go and take a bike wheel, leave it there, start spinning, you realize that you must put in energy to it. Okay? Okay, so the energy linked to rotational energy is given by this equation. Okay. Half m v squared. Right. That means the sum of all the velocities with relation to a point or center of rotation point. And we know that v equals r omega. Did you all register that v equals r omega? The velocity is radius times omega. Okay, you did that, so cool. Yes, you're registered. So once you have that, then you can have this equation, half m r squared omega squared. Okay. So the total kinetic energy is hence the sum of all these points, which gives you this equation. Mathematically, it's not that difficult. Moment of inertia. Moment of inertia is a concept that we introduce to decide if something is hard or easy to spin. Something is hard or easy to spin. So, the kinetic energy, right, can be written as this, which means that I is defined. It's a defined term. That means it's something that we introduce to make the calculations easier. Okay, as this. Okay. Any questions? It should follow from the previous slide quite easily. You can see, because mine is one slide, you have two on one. You can see quite clearly how that transforms from the previous one to the next one. Okay. So the fun part here is, in this chapter, is how to find a moment of inertia for many different objects. That's the one that really pulls your hair out the first time you try it, and pulls the rest of your hair out the second time you try it. Right? No kidding. Hopefully, I will make it a less hair-pulling experience for some of you. Some of you who are mathematically very strong, it will be actually quite a walk in the dark. Okay. Right. So the idea here is, how do we do this? Right? Is that we want to consider consider every point on the object that we're considering. Let that point have a mass that's close to 0, and we multiply that by r squared and we sum that whole thing up. Okay, that's the idea of trying to find moment of inertia. But you see that this summarizes very easily into this. Right, summation sign of delta m is just integral dm. Mathematically, that's how it translates from a discrete case to a continuous case. Right, because writing a summation sign with limit m is just difficult. This is much more elegant. Right. And next is that we can realize that dm is simply just density times dv. Right, not a big issue. Usually we just stick to this equation over here. Okay, this one you can read on your own. Do note the units, right? Do note the units. something to say. Okay, the moment of inertia, I think this is quite important, is a measure of the resistant object to changes in rotational motion. You have learned about inertia of mass, right? Mass inertia, I've mentioned it a while ago. Right, it's the resistance to change in motion, right, which is quite, in this case, equal to mass itself. Right? So inertia is more or less like equal to, proportional to mass. So here we have something else that we call moment of inertia. Okay, it's then the propensity to resist changes to rotation. Okay. So the concepts can be mapped quite quickly over from linear motion. All right, the first example to really warm us up into the whole thing is this. And actually, it's not a very good warm up in the sense that I already chose something a little bit challenging. Okay. So if you have a pen, some of you like to spin pens, right? You realize that if you take your pen like this and you spin, you turn to move it, and you take it like that and you try to move, which one is harder? When you put it at one end, right? Of course, there are other issues, but the point is, even if you put it horizontally, right, that will reduce the weight factor. Do it like this. You realize if you take it horizontally and you take it at one end, right, of course on the table and you spin, you realize that it's actually easier to spin from the middle than from the end. And there are ways to quantify how difficult that is. Okay, and that's what we're trying to do today. So here in this question, we put the axis of spin h distance away from one end of the stake. Okay, h distance away from one end of the stake. We can say that the mass m depends on dx by this equation, where lambda is the density of mass, right, per unit length. Mass per unit length. Right. So once you know that it's a mass per unit length, the linear density is essentially just mass divided by the length. Okay. So this is something like linear density. It's not like the real density was mass divided by full volume, but mass divided by the length. Okay. So we are assuming that this rod is pretty small. Right? The cross-sectional area is pretty small compared to the length. So let's go using this equation. So everything where my arrow is pointing is a given. Everything else to the right is what you need to figure out how to do. So let's start by the conversion. dm, we have to convert to dx through this equation, right? Because you know that this is given by dx. So dm becomes mol dx, not a problem. R, because now your r is given by x away from this point 0. You can change r to x directly. Not a problem because x is r away from origin O. Okay? Once you have this, the simple mathematics suggests that the maximum is L minus H over here. And the other side is negative H. Important, huh? There's a negative here. Once you integrate, you have this, sub in the values. Looks difficult, but it's not. You get this. Okay, so this is the general equation for spinning a rod about an axis like this, not through the rod. If you go along the rod, then the inertia is almost 0. So we generalize, right? We generalize, and we see that this is very nicely applied to some of the cases. Right? Special case when you are spinning at one end like this, H becomes 0, L is the whole thing. Right? H becomes 0, you get this. So this conforms with if you look at the textbooks, right, they usually start with the middle case first, right? Most textbooks start with the middle case first, and then this case, and then they give you the general situation. But in Olympiad, we share around, we give the general case so they can solve all situations, then we confirm the cases. So these are some of the numbers that you may want to like check to memory, right? Okay. So that when you solve it, you realize that, oh, okay, this is roughly like that. Okay, so this is expected. So you realize that when I said when you spin by the middle, right, it's a lot easier than from the side. In fact, it's about 4 times easier, right? Because the moment of inertia is 4 times smaller. Okay. Questions? Okay, it gets harder. This is the warm-up. All right. Calculating a hollow or solid cylinder, spinning about its center. Okay, so once the blue line is the axis of rotation and you're spinning about it. So this is like your water bottle here, spinning. Okay. So how would you go about this? So what we did just now is to relate m to x. But remember that in the end, we always want it to consider from. We're going to use symmetry to simplify our calculations. So here the symmetry is obviously r from the center of the axis, right? And we know that the total mass is 2 pi r times L. Right, if you take a cylinder, right, it's just 2 pi r times L times the density. So here you would use 2 pi r times L times density dr to find dm. Okay. So what is this dm? I say again, be very careful. This dm is this shaded red area, because I saw some of you, what do you mean? So, okay, good. I can read your faces. This dm is the mass of this shaded ring here. So a full mass would be the sum of all the rings, or rather cylinders of various radius, from the smaller one to the bigger one, to the next bigger one, to the next bigger one, to the next one, to the full length, and you add up all the masses. Clearer now? Yes? No? Okay. So what I'm doing is I'm taking a toilet roll, and the next bigger toilet roll, and the next bigger toilet roll, and next bigger toilet roll, to form this shape, to form a toilet roll with certain thickness. Right? So I take the mass of the smaller one, which is given by this. So if your radius was initially 1, you get 2 pi 1 row, and then the next one will be 1.1, then 1.2, 1.3, different radius. Okay? Clearer? How do you do this with experience? That's why it's hair pulling. When I introduce to you that, they're always like, oh yeah, it's obvious, it's at a stage of understanding. But when you're given a new shape to think about, that requires a little bit of creativity and all experience. Okay. Right, so back to this. The equation, as we know, is I equals to integral of r squared dm. And dm, we want to use a smart dm to solve this. We realize that a smart dm would be to consider masses with various r's, because r is something that we have already, right? We're going to use it to dr. And so you notice the first one, you have dx, because everything is in terms of x. You change dm to x. The r squared is then x. Here, everything is in terms of r, and you have a dr, then you can actually integrate it. So you want something like that in your equation. Put together, you have this. The rest are just mathematics. Sub in, and you get this monster, scary looking thing. Don't worry. Right? This and this simplifies into this liquid. This is the mass itself, the full m, because if you have the maximum R2 and the minimum R1, right? This whole thing is the mass itself. So this gives you half m, R2 squared plus R1 squared. Okay? Very painful. I see some of you. Like boring, huh? Is it boring? Too slow? Too fast? This seems okay, right? So you have thin cases where your R1 is more or less equals to R2. That's your thin cylindrical shell. So both of these becomes R, right? You get the nicest moment of inertia around, which is mr squared, just mr squared, happiest ever. Okay? If I give you a mass thin shell like this, which is your toilet roll of 10 grams of certain radius, just mass times radius squared, then you get this. Right? But if you're something that's full, so you have a solid aluminum bar like this, or cylinder like this, then you have simply this. Okay. So these are the nicest. The cylinders are actually the nicest to spin. Okay. Okay. Okay, this is an important point. And the last line is an important point. Something like that. Right. So, okay, we can get to that later on. Right. Next, let's calculate a solid sphere about a center of axis. So it doesn't matter which axis you choose because it's a solid sphere. Right? Anywhere you cut it is the same as long as it passes through the center. So now this is going to be a little bit difficult. You define R, small r, as radius and x, where x is the distance from the center along the axis. Okay? What is a good dm to choose? Right? What's a good dm to choose? Somebody say, why not we change it to dr? Right? Why not change to dr? But which r are you talking about? Right? That would be very hard to actually do. Right? Dx is actually somewhat easier. So this requires experience. Right? If I give you this as a question right from the start, after introducing you just the initial idea, I believe and presume most of you would have difficulty here. Okay. So dm becomes density pi r squared, where r is this disk itself, dx. Okay. And we know that r, the distance of the axis to the surface of the sphere, that means perpendicular distance. R is this perpendicular distance. It's given by r squared minus x. We have this. Okay. So here you must do and use what you have learned before, like what we worked out here. So this makes it doubly difficult, really. No kidding. For a solid disk, this was our result. Right? Half I, right, in the previous slide, look to the right, this one. This one. I equals to half mr squared. That's how you get this first part. So di becomes half dm r squared. Okay. And then r you change to dx because you want to integrate it over the whole of the x. So subbing in. So here is a slightly different tag. If you realize it's slightly different strategy from everything else before. Everything else before we use I equals to integral of r squared dm. Right here we use di. Interesting, huh? So you must know with some experience when to swap the method of approach. So di, if everything here in terms of dx, let it go. x is r2 minus r, sub everything, then after it's just mathematical. Okay, so this requires some experience, no kidding. If unsure, just practice, right? There will be a lot of practice questions possible. Right, done. So these are some of the things you talk about: a rod, a cylinder, and a sphere. Of course, there are other shapes possible. Okay, of course, there are other shapes possible, like a chair, for example, spin about one corner. Right, but that's tough, right? And we are just always talking about using symmetry, always being about the center. What about it spin not about the center? Right, so we have something called the parallel axis theorem. Oh wait, so that one you can do. It's not a problem, right? Let's move on to the parallel axis theorem. So if this is the center of mass, right? So actually just now all those examples were spun about the center of mass. Do you agree? The axis of rotation spins about the center of mass. Yes? You realize that the cylinder, other than the rod, the cylinder and the sphere is spun about the center of mass. And even for the rod, the special case where it's spun about the center is through the center of mass. Actually, you can use the parallel axis theorem to prove these two cases for the rod. But let's talk about it a bit more. So if it's your rotation axis is not through your center of mass, but a certain distance away, d, right? We can actually say something about it. Okay, we'll show. Let's prove it. Wow. Just math. So this is the center of mass. This is where you spin it now, right? So the new moment of inertia is r squared. Is r squared, right? dm across all points. Okay, it will be x squared, the new x squared and the new y squared. But the new x squared and y squared is just essentially this. Ouch. Ta-da. Magic. So what does it say? The conclusion is simple. That the new moment of inertia, when you spin it a certain distance away, is essentially the previous one times the mass times d squared, where d is the distance away from it, which is surprisingly simple and elegant. Right? But if you actually work through all this, the math, right, you get this quite nicely. Okay, moving on. So example, just now the rod that we have, right? So through the center is actually ml square over 12, right? Agreed? Using parallel axis theorem, now we split it on one end. The distance away, h squared or d squared, is actually L over 2. You add together to get ml squared over 3, which is what we have proven earlier, right? Using working it from the ground up. So what is good? What is good? My suggestion is this: in your Olympiad attempt, right? It is good to memorize the moment of inertia for some objects and just apply the parallel axis theorem, which makes things a lot easier. Okay? Right, for example, for the sphere, if I say I spin the sphere about a point on the surface, you just take this plus mr squared. Done. I don't have to work it out from the beginning and go through all this pain. Okay. What about this? Answers there in writing form. Oh wait, that's not the same thing. That's for the sphere. The cylinder one, we have mr squared, or half mr squared. Right, the h is m, then r squared, so it's 3 over 2 mr squared. So here, this one should be 3 over 2 mr squared. Okay, this is 1 half a is just like that. Not sure. Any questions here about any other workings? The one on top should be 3 over 2 mr squared. Yeah. Questions? Okay. Oh, now we come to something a bit more painful. It's called the perpendicular axis theorem. Oh my god. It's not the same, huh? Parallel axis theorem is not the same as perpendicular axis theorem. Okay? But let's be very careful. It only works for plane figures which are 2D, not negligible distance, thickness, sorry. So let's read it very carefully. The sum of moment of inertia about any two perpendicular axes in the plane of the body is equal to the moment of inertia of axis through the point of intersection perpendicular to the plane of the origin. What does this mean? It means that if you spin the object about y, you have certain y-axis, you have a certain moment of inertia. You spin it about the x-axis, you have certain moment of inertia. These two moments of inertia you add together will be the moment of inertia across for z. Right? Okay, so that's basically what it means. Let's try. Find the moment of inertia Ix of the disk about an axis through its center in the plane of this. So since the moment of inertia of the axis through the center of this is given by half mr squared, right? The moment of inertia through z is half mr squared. Do you agree? Yes, right? Did you get what they are trying to do here? They ask you to find the moment of inertia of x. You do not know that. To do that would be extremely difficult. Not extremely, it would be difficult. Not extremely, but difficult. Right? But you know that the moment of inertia through x and the moment in y must be the same because they both pass through the center. So they are similar. And you also happen to know the moment of inertia of z because you have already previously calculated it on one of the pages before. This one, the disk. Okay, this disk. No, the cylinder one. It's the same thing. The cylinder and the disk is essentially pretty much the same. One has a big thickness, but the other one has not. And there you have it. Right? Because the perpendicular axis cannot be applied to cylinders, you have no choice. That's why you apply to a disk. Right? So Iz equals to Ix plus Iy. Iz is half mr squared. Since these two are the same, you got that quantum. Simple. If you do not believe me, you can try to figure this out from ground up through the I equals to integral of r squared dm. And you find that it will be very, very, very painful. Okay? So yeah. Ta-da! Okay? Homework, go and try this for fun. Right? Try to prove this. Right? It's a good exercise. The rest of the fun stuff coming up. Rod at the end, these two are easy. Solid sphere, we guided you through that. And then you have the thin sphere, right? Which is something that you should also try and do as homework. Even if you cannot do, you can go online and find. Because these are such classical objects, right? The thin shell, all this, right? Google is there. Okay, you can try, cannot get it, go and Google it. The method will be there. Right. Okay, let me pause the video if not it's too long.